Okay, so in the last class we have discussed about flux switching permanent magnet motor drives. Okay, so now we will try to discuss hybrid excited permanent motor drives here. The concept is more kind of similar to that of the flux switching permanent motor drives. So here we'll try to discuss the first operation, then we'll try to proceed further here. Okay, so this is the corresponding diagram of the permanent hybrid excited permanent motor drives. By the word we can see that hybrid excited here. So we know that field winding can be excited with two ways here. One is electromagnets, that is with supply, with the DC supply, permanent DC supply, and whereas with another way is permanent magnets. So here in the normal regular machines, like in DC motors or that in regular machines, we use this field winding electromagnets, whereas for special machines we introduce the concept of permanent magnets here. So now comes the combination of these two here. We call this as a hybrid excited permanent motor drives here, where we combine we include both the field winding as well as permanent magnets here, so that we can able to achieve some of the special features with that here. Whereas with the inclusion of permanent magnets, we can able to control the flux, we can also control the field variations here, whereas by including this we can able to achieve all the things here. So we can able to see that by incorporating the hybrid excitation of the stator PMOs here, we can able to directly control the air gap flux. Okay, and here even we can able to achieve the strengthening and weakening of the air gap flux also. So ultimately we can able to control the flux, so that even we can able to design the motor as per our requirement here, load requirement here. Okay. Okay, now we will try to see that construction in the structure or in the construction. What we can see that here the red ones, okay, this is, which is already specified here, this is DC field winding, okay, where we can able to get the electromagnets, similar to, we can say that electromagnets here. And first basically we can able to classify this here, the green color which we see, that this is stator, and this salient pole, that is rotor here, the outside port, and center one we can say that this is shaft. Okay, and here in the stator, okay, as the heading suggests that it is stator, okay, permanent magnet, stator permanent magnet motor drives here. In the stator I am incorporating the permanent magnets here. I am incorporating the permanent magnets. Where I am keeping these permanent magnets, the red color, which is, we can able to see that these are permanent magnets here. Okay, this red color which we see that this is permanent magnets. These are all permanent magnets here. And the pink one which we see that this is field winding. Pink color which we see that this is field winding here. With the field winding only, when we excite this field winding only, it acts like a electromagnet here. We can see that this is the north pole. This is an this is the north pole and south pole, which you see that this is for the electromagnets. Whereas for the permanent magnets also, you can see that there is a different poles are formed here. Okay, so here indirectly I can say that both electromagnets as well as permanent magnets both are included in this type of rotor here. And coming to the okay, so ultimately we can able to get the air gap flux control can be achieved here. Okay, so let me try to tell in detail about this stator as well as stator also. So the points what we already discussed, we'll try to discuss again. Okay. So armature winding here, coming to the armature winding, it is similar to that of the conventional machine here, normal machine here. So the main purpose of armature winding is to carry the current and to produce torque here. Okay, we'll try to discuss one by one part here. Coming to the DC field winding here, so here this field winding creates a magnetic field here, which you already know that normal this is electromagnet. And coming to the permanent magnets here, it produces a constant magnetic field here, because permanent magnets we are not exciting here, it is generated, flux is generated on its own here, and it's depending upon its material quality and other things here. So, and coming to the rotor here, what is the shape of the rotor here? It is in salient pole structure, projecting pole, which you already seen that in the just now here, it is in salient pole structure here. Okay, it is in similar to this salient pole structure. And okay, and coming salient pole structure, and it is also typically it is made up of laminated steel here. Laminations, everyone knows that what is the laminations here, to reduce the eddy current losses. In every machine, eddy current losses will be existing, and we try to overcome that. Okay, The salient poles are designed to interact with the magnetic field produced by the stator windings and to create a torque here. The why there is a need of salient pole, because so it has to interact with the magnetic field produced by the stator winding, and ultimately we need to generate a torque here. Torque is nothing but this which will make the motor to rotate here. And here, in addition to, there is extra term called air gap. Extra air gap is required here. Okay, so what is the purpose? Let me show in the diagram here. First, it is the purpose of the extra air gap is to provide the interaction between the stator and okay, the permanent magnet and electromagnetic interaction here. Okay, I will try to show the air gap here. Okay, this portion where you see here. Okay, the portion which you see here. Okay, yeah. So this portion, the small extra air gap is provided here in all the 4 cases. The small extra air gap provided here, and the purpose of the extra air gap, as we discussed, that what is the purpose of this extra air gap? Okay, the purpose of the extra air gap is to create a space for the rotor and stator currents where the magnetic field interaction occurs here. And coming to that, how this field DC field control can be achieved here. We just saying that okay, I can able to strengthening the magnetic effect, and there are 2 possibilities here. So strengthening, okay, the flux can be increasing and flux can be decreasing. And when it is increasing here, we can say that strengthening magnetic field, and when it is decreasing here, weakening magnetic field here. By indirectly, when flux is controlled, and ultimately all the necessary speed and torque, everything can be controlled here. Okay, and this is achieved with the DC supply, and this is what we see, that by incorporating this power electronics equipment, we can able to see that how the strengthening and weakening effect can be done here. So you can see that this is a diagram which represents a simple switches here. Okay, 4 different switches is there. This is a combination of BJT and reverse switch here. Okay, a freewheeling diode, freewheeling switch here. BJT with freewheeling switch here. So the purpose of the freewheeling switch is to operate in the reverse direction also. Okay, and here 4 switches are there here. We can say that this switch can be any type of BJT or MOSFET or IGBT or at least diode or whatever it is. Okay, ultimately we need to have a switch function where we can be able to control the direction of power flow here. So here this is the one which is representing in between. This is DC field winding here, and we will try to see to that we have to control the direction of power flow. Okay, direction of power flow can also be controlled here. We can able to, by increasing the DC supply, one way here it is how it is controlled, that we can able to increase the, by increasing the current, flux can be increased. By decreasing the current, flux can be increased. This is strengthening, and even we can able to change the direction, polarities also. Polarities can be reversed. How these polarities can be reversed here? That is with this. Okay, yeah, let me try to show the set here. So here when S1 and let's assume that the first case here, even the same is explained in detail in the subsequent pages also. When switch S1 and S4 are on, when S1 and S4 are on here, when it is on, and this is also on here, then in situations the direction of current flow will flow from positive side to S1. Okay, this is plus, this is minus. Direction will flow from S1. Okay, let me try to write here S1. Next DC field winding. Next S4, and to negative supply here. This is the direction of power flow. So that let's assume that this is plus and this is minus here. So instead of that, if suppose in the second case here, this is case 1. In case 2, when S2 and S3 are on, when S2 and S3 are on here, in such cases what actually happens here? So the power flow will flow from this. Okay, the power flow will flow from, okay, yeah, let's assume that, okay, yeah, in case 2, okay, just I erase for our easy understanding here. When S2 and S3 are on here, so what is the direction of power flow here? It will flow from the S2 switch again to the DC field winding, again to S3 and back to here. This is plus minus. Okay, so now here previously the supply is from plus to minus here. Now what is actually happening here? Direction of power flow is reversing here. So I guess in the other subject class also you might have studied here direction of power flow, 4 different modes of control here. Okay, motoring, braking, and reverse motoring, reverse regenerative braking here. So here I am indirectly using the switches, 4 switches to operate the give the polarity in the reverse direction. By changing the polarity, by changing the direction of current here, by changing the direction of current, what is happening here? Polarity changes. So in this manner, the north pole, south pole can be changed to south pole, north pole also. So here I am attaining two cases here. One is the flux can be strengthened and reduced, as well as, and flux polarity can also be reversed here. Okay, and coming to the next one here. So the same is explained here. Just for understanding, the same is explained here. Just one is, and here in the last class we have discussed about. In the last class we have discussed about this hybrid flux switching permanent motor drives here. Flux switching permanent motor drives here. Now even we will try to incorporate this hybrid excitation concept, as we have discussed in the other classes, that if you add any new thing here, that will be becoming as a special mission. So we already have flux switching permanent motor drives. We already have flux switching permanent motor drives here. Now here to this existing flux switching permanent motor special mission, I am adding here hybrid excitation concept. That's it. Whatever we discussed in the previous classes regarding the flux switching, just I am adding a concept of hybrid excited. What is hybrid excited? I am incorporating permanent magnet, as well as I am also adding, the already permanent magnet is already there here. I am also again adding the DC field winding. I am adding the DC field winding here, and then just once by adding this DC field winding, it will be converting as a hybrid excited. And what are the features that we flux switching concept that is we are using here, the same can be implemented here, and it is becoming a new type of machine here. So together we can able to conclude this as hybrid excited flux switching machine. Let me try to briefly discuss what we have revised in the last class, okay, so that you can able to understand here. So this is the corresponding diagram here. You can see that previously we can only see only the yellow line, okay. Previously we can able to see only, yeah, okay, this is the flux switching motor types drives here. We can able to see only yellow lines here now, and these are the three different ways here. We already discussed that one is with original, and second one is with reduced alternate poles, and third one is alternate poles with reduced magnets here. So the same concept we here also we will try to use here. Okay, same concept also we are also use here. Only thing, what is the difference here? You can see that in addition to the yellow line, what we have seen that, okay, here also I am using one more line, that pink color line, which indicates that this is the DC field winding. Once DC field winding is introduced, electromagnets are incorporated. And what is this red portion? That is permanent magnets here. So we have this both DC field winding and permanent magnets. So that together I can conclude that this is hybrid excited. This can be computed, and rest everything is same what we discussed here. So together we can conclude that hybrid excited flux switching permanent motor here. So the operation is as the flux is switching, its flux switching takes place for the motor operation. The torque is generated, and that's why it is called the flux switching permanent motor drives here. Okay. So constructional parts, everything is same here. Stator, it has armature windings here and DC field winding, and we said that permanent magnets also incorporated here. So major difference what we need to consider here, the size of the side might be reduced. Permanent magnet size is reduced compared to the standard FMSM to make space for the DC field winding. Only thing is, as design is equally important here. Okay, how best machine we design is not, in addition to that, the size and complexity also matters here, efficiency. So in design spaces here, permanent magnet size can be reduced here in order to accommodate the DC field winding here. Rotor is by default, it's a salient pole type here. So whatever the diagram that we have gone through in the last class, I'll try to add one small point here. We already discussed that this is DC field winding, and this is the permanent magnets, okay, and this is armature winding. This part is rotor, and this portion is stator, okay. And the rotor is we have two fluxes here, okay. This is DC, okay, this is armature winding here, and when we discussed that there is a close path between the rotor and stator, and in this manner, and from two different portions here, from the figure 1 and from figure 2 here. Okay, in the first figure we can able to see that the flux is flowing from the north pole to the south pole, and it is forming a close path, whereas in the second case here the flux is flowing from the south pole to the north pole. This is forming a different case here. So in this manner the flux switching concept takes place here, which is we discussed in detail in the previous classes. Now here in the hybrid excited, what we need to add extra, the only difference you can see that here we can see that there are two different colors here, Okay, we can able to see that what we need to highlight here, only two different colors here. The thing is that if there are I can able to classify this hybrid excited flux switching permanent magnets into two categories. One is, so two ways here. One is flux strengthening effect and flux weakening effect. When permanent magnets and DC winding, and permanent magnets and DC winding both are in same direction. In permanent magnet and DC, when both are in same direction, then what happens here? The flux strengthening effect takes place. We can say that flux strengthening effects takes place, and this is the corresponding diagram. You can see that both arrows are in the same direction. So both there is a close path flux forming between the both stator and rotor in the same direction with the effect of DC field winding as well as permanent magnets, and that's why we can say that the first type is flux strengthening effect is taking place. Whereas you can see that in the second type, here you can see that one, okay, the red line which is indicate and the green one which is indicate with the opposite case here. So here the flux weakening effect is taking place here. What is the basic thing here? Here it is in permanent magnets and DC winding, field winding, better say that field winding, both are in opposite direction. Okay, both are in opposite direction, so that what happens here, the net amount of flux reduces here, and we call this as a flux weakening effect. In this reason, in this way, we can able to just add the already existing concept to the flux switching permanent magnet, and we call that as a hybrid excited flux switching permanent magnets. Okay, and same, just will again, and what we are going to achieve, main thing. Okay, ultimately when we are doing something here, we need a requirement here. Why there is a need of this, again, to incorporate hybrid excitation in the flux switching here? There are main two reasons here. As we discussed that, we can able to strengthen the flux as well as weaken the flux here by increasing the flux here. So torque and power input can be improved. This is a major point here. Ultimately, we need to see that the output efficiency has to be increased here. And how the output efficiency increasing here? I am including the field winding, so that it is converting into hybrid excitation. With this, when the strengthening effect here, the increase in torque and power output, ultimately we can able to improve the output power as well as output torque here. Sometimes the weakening flux can also be useful here when both are in opposite direction, as you see in the both cases, in the above previous case here. So when the resultant amount of flux decreases here we can able to increase or extend the speed range here. So we can able to operate wide range of speed here. We know that even what are the fans that we are using here, we always expect the fans to operate in the wide ranges here. So for smooth control, somewhere from 300 rpm to 1500 rpm, wide range speed control can be achieved even in the hybrid excited with the flux weakening effect. These are the major reasons, or else aim here. What is the aims here? How to improve the torque and output power, and how to improve the speed range here. With the strengthening effect, we can able to increase the torque and output power. By the weakening effect, we can able to extend the speed range here. Next here, what we have discussed in the last class, just I'll add one more point here. Same here. Again, this flux switching permanent magnets are classified into three types here. Original one and alternate poles, and alternate poles with reduced magnets here. This is the original one here. With each stator winding has a separate permanent magnet pole here. Okay, and for each winding, okay, each pole we have this winding here. Okay, armature winding is placed here. Whereas here, in the second case here, alternate. In the second case here, alternate case here, you can see that the winding is done only. Okay, the winding is done only for the alternate poles here, not to all the poles here. And the third case here, then, so as I'm not using this permanent magnet here, why there is a need to incorporate and add extra cost here, and that's why to reduce the cost here, even in the alternate poles here, the permanent magnets are also reduced. This is we discussed in detail in the previous lectures here. Okay, and ultimately we can able to have different concepts and different applications with three different cases here. As the permanent magnet cost and availability is very high and availability is very scarce, so that even we're trying to reduce the permanent magnet usage for this type of motor here. We can able to classify into three types. This is the original one, this is the alternate poles, and this is the alternate poles with reduced magnets here. So this is all about the conclusions of this hybrid excited permanent magnet motor price. We'll try to discuss the next concept in the next class.